And now over here, and then we'll hide that, and you're ready to go. Can you see that, Nat?
Yep, I can.
Fantastic. Okay, people ready?
Yeah. So today we are going to talk about principle of MRI. Acquisition of MR images consists of 4 distinct stages. The first one is body part is placed in a strong magnetic field. Second, external radio wave frequency is applied to the body part. Third, external radio wave frequency is switched off. And finally, the body part emits radio wave, which is captured by computer, and image is created. So we'll go through all these steps today in detail. But before that, I would like to recall production of X-ray that we learned a few weeks ago. X-ray is produced when the moving electrons are suddenly or abruptly stopped by the metallic anode. There are 2 types of X-ray radiation. One is characteristic radiation, and the second one is Bremsstrahlung radiation. Characteristic radiation is produced when the moving electron displaces electron of anode, whereas Bremsstrahlung radiation is produced when the moving electron changes its course, loses kinetic energy in the form of electromagnetic wave X-ray. If you have noticed, X-ray production occurs in the outer, you can't see the cursor, in the outer part of the atom. Whereas MRI is, the MR images is acquired from the inner part or the nucleus of the atom, and more precisely from the proton of the nucleus. In high school, we learn matter is made up of atoms. An atom consists of centrally located nucleus, which is primarily consists of neutron and proton, and surrounding electrons, which moves along their orbit. So moving part is electron, and the proton and neutrons are in the centrally located nucleus, which is stationary. And in university, we learn quantum physics, which says that electron moves, but nucleus is also not stationary. For example, proton moves in its own orbit. It's a particle, it has got mass, and it's positively charged. When the positively charged particle moves, it exerts magnetic field around it. That means every proton is tiny magnet, and we are made up of millions and millions of protons. So we have magnet on us. For example, more than 60% of our body is made up of water, and 1 drop of water consists of 6.7 10 to the power 9 protons. So the question may arise, if we are made up of tiny magnets, why we are not magnetized? And the answer is that nature doesn't want us to be magnetized. And all these protons are randomly distributed in such a manner that they canceled out their magnetic field, and the net magnetization becomes 0. Then the scientist thought that what if we align those tiny magnets in one direction? Can we be a magnet? And that is the first part how we acquire MR images. That is, we put our body part in the external magnetic field, and those tiny magnets align along the magnetic field. And they are right, those scientists were right, that when we put our body part in the external, very strong external magnetic field, all our protons aligned in that particular the external magnetic field. But later on, they found that half of these protons align parallel to the external magnetic field, and almost half of them anti-parallel to the magnetic field. So effectively, they are just neutralizing the magnetic force of each other. I said word almost because they found that slightly greater number of protons align parallel to the external magnetic field. 7 in 1 million. If the strength of external magnetic field is 1 Tesla, 7 protons align in the 7 more protons align along the magnetic field, that is parallel to the magnetic field, as compared to anti-parallel, which means the person gets slightly magnetized. And this weak magnetization is used to create the image in MRI. And this magnetization is along the axis of the body, and it is called longitudinal magnetization. But there is a small problem here. This weak longitudinal magnetization is along the direction of strong external magnetization. So we can't extract this weak magnetization to create image. It's impossible. It's difficult. Then they also noticed that when we put our body part in the strong external magnetic field, it's not only they aligned along this line, but also they exhibit a circular momentum. The Hubble, like this, perpendicular to this magnetic field. Okay, this momentum is called precision. And now they are happy that now we have another transverse magnetization. It is not aligned with the external magnetization. So maybe we can extract that magnetization and create the image. But later on, they realized that these protons, they moved chaotically. There is no synchronization there. So they move chaotically, and effectively they cancel out their magnetic force, and the net magnetization becomes 0. Again, nature doesn't want us to be magnetized. So how it occurs, I'll show you in this. Yeah, it's a small demonstration. These are all dipoles of the protons, external magnetic field. So this is our longitudinal magnetization. And this movement, this transfer momentum, the frequency of this depends upon the strength of external magnet, which is B over here. And the constant is gyromagnetic ratio, which is specific for the specific material. So we can calculate the frequency of this circular momentum with the equation called Larmor equation. So for hydrogen atom, it's 42.58 megahertz per Tesla. And it's important to know this frequency, because what we found is that if we apply same frequency, if we give this external frequency, Larmor frequency to the proton, it absorbs that energy and it get energized. And that is second stage of our MR acquisition. External radio wave frequency is applied to the body part. The external radio wave frequency is applied. That means that is Larmor frequency is applied. So now these arrows are just a vector of the proton. So when we apply external wave Larmor frequency to the proton, some of these protons get energized and they flip around towards the antiparallel side, which causes decrease in longitudinal magnetization. Okay, so how it occurs? So we applied external wave frequency and it's decreasing, and it just flip around antiparallel side. Okay. Similarly, external wave radio wave Larmor frequency, so it's chaotic, it's not synchronized, but if we applied that frequency, it became synchronized, and the transverse magnetization start to raise. No? So how it occur? So this is called resonance. Is it clear? Any questions?
So the Larmor frequency that's applied, is that the Larmor frequency of water?
Water.
Okay.
Yeah. And the third stage is external radio wave frequency is switched off now. This radio wave frequency, when you give radio wave frequency, the proton absorb that energy, and when we switched off, the proton exert that energy in the form of radio wave frequency again. Okay. So how it? So when we stop radio frequency, this antiparallel, those energized proton which flipped in the antiparallel direction, goes back to their original position, and the longitudinal magnetization start to raise. And during this process, the tissue start emitting radio waves. And this process is called T1 relaxation, also called spin lattice relaxation, or we can just say T1 relaxation. And the longitudinal magnetization is complete here. Similarly, when we stop applying radio wave frequency, they are synchronized here. Again, they become chaotic, and they start emitting radio frequency. And the transverse magnetization keep on decreasing. So it's called T2 relaxation. So is it clear?
All right, I didn't quite get the difference between T1 and T2. So what?
No, I'll come there. In
Okay.
T1 weighted image and T2 weighted image is different.
Yeah.
This is T1 relaxation and T2 relaxation. So maybe I'll just go, yeah. So T1 relaxation is all about longitudinal magnetization.
Oh, okay, yeah.
So when it flip up and goes to its original position. T2 relaxation is transverse magnetization, where initially it is synchronized and it's synchronized that and later on when we stop radio frequency, it became again chaotic, and this magnetization keep on decreasing.
Okay, that makes sense. Thanks. Yeah.
So this is a graph of longitudinal magnetic relaxation. So initially it's 0 and it keeps on increasing. Finally, it becomes plateau here. And different tissue has different longitudinal relaxation. And the contrast between, to differentiate the tissue, we'll take a longitudinal relaxation at a specific time. So generally, longitudinal relaxation is high when when the longitudinal magnetization is at initial stage, okay, as compared to the late stage. This is time, this is signal intensity. So if the computer take image from this stage, it will be T1 weighted. It will be strong T1. And this is transverse magnetization. Initially it is high and it keeps on decreasing. And T2 relaxation is more, not initially, but later on. So when we take image from this stage, it will be T2 weighted, strong T2 weighted. If we take image at this stage, it will be less T2 weighted.
So the only difference between T1 and T2 is time?
Yes, I'll show you later on. So this is a combined relaxation. So it's T1 relaxation, here T2 relaxation, okay? Because this T1 and T2 relaxation is two different processes, but at the same time, they occur simultaneously. And finally, those radio frequency that is emitted by the body part is captured by computer and the image is created. So here it is. So here is two different issue. It's T1 relaxation, it's T2 relaxation. If we take image at this stage, it's less T1 T1 differentiation, it's more T2 differentiation, and this sort of image is called T2 weighted image. On the other hand, when we take image at this stage, where T1 differentiation is high compared to T2, it's called T1 weighted images. So what I'm trying to say is that T1 weighted image also has T2 component. It's only the intensity is low. So it's just, we can take image from here. It is completely T1 weighted without T2. So we can ask computer to take what kind of image we really want. So what will happen if we take image from this part of the graph where T2 is also less and T1 is also less. And that sort of image is called proton density image. Because this image depends only on the amount of proton and not the relaxation. Now we'll talk about MR contrast. The most commonly used MR contrast is gadolinium, but gadolinium is very toxic. So it has to conjugate with DTPA, and then only you can use it as contrast. Gadolinium has paramagnetic property, which means it decreases relaxation time of surrounding protons. So for example, we have two different tissue. A, for example, it's tumor. B is normal tissue. And we want to differentiate tumor from the normal tissue. If we add gadolinium in A tissue, the relaxation time will decrease and this curve shift towards left. And there is wide differentiation between A and B tissue, and we can differentiate the tumor from normal tissue. This is how the MR contrast to work. For example, here is a tumor, right ovarian mass, and it's a right ovary. And the gadolinium contrast is injected, and you can see the differentiation between ovary and the ovarian mass. So this is a brief overview of MR images. In next class, we'll talk about time of repetition, time of echo, and spin echo images. We'll also talk about gradient echo, star and flare images. Thank you. Yeah.
Yep, that's a lot. But just a quick question. So on the different strengths of MR images, is having a stronger, like some MR machines are 1 Tesla or 1.5 Tesla and some at 10. What's the difference there?
That's the signal intensity. For example, if you have noticed that when you put our body part in external magnetic field, they align along the direction of external magnetic field. And I said, if it is 1 Tesla magnet, around 7 protons align parallel, more parallel than anti-parallel. And that 7 proton is responsible for image creation. If we increase to 2 Tesla, then there will be 14 protons. That means the strength of signal is twice and the strength of, if we have a good strength of signal, we can differentiate the tissue much better.
Yeah, I also have a question.
Yeah.
So yeah, you showed an image of the proton density imaging. And what do they actually use that for? We usually just get the T1 and T2. So what's proton density imaging used for?
Usually proton density is used for tumor again, soft tissue tumor.
Yeah.
So to differentiate from the non-malignant benign inflammatory region, for example, inflammation.
Yeah.
So the proton definitely, whenever we're saying proton here in the context of MRI, it's water always, mostly water. So if the water content is high in any sort of lesion, that is usually benign lesion, because cellular content is less, water content is high. So to differentiate these two major type of lesion, we use proton density. Yeah.
You showed some of those graphs there, and on one of them it had the T1, and then it progressed into the T2. But then in another graph, it had the T1 and the T2 started partway along it.
Yeah, I got it. Yeah, yeah. The graph I showed, that first T1 and then T2. I just wanted to convey the message that these two processes are actually separate, but at the same time it occurs simultaneously, and it should be read as a simultaneous process. You can't just ignore one and take another. That is the reason that I showed that one, but they keep on changing.
Yeah.
It's a more computer work. I just try to simplify as much as I can. Yeah, it's the computer that we don't have to do all these graphs. It all, yeah.
It's just, yeah.
Yeah.
Simultaneous.
Yeah.
Cool.
But they are separate. They are not
Yes.
one. They are just totally separate thing. But it all
Same time.
simultaneously. Yeah.
Electrons, also tiny magnets.
But the weight, I mean, the mass of electron is so tiny. Yeah. At least in the MRI, we don't consider it.
Thanks so much again.
Thank
Yeah,
you.
it's really good.
Yeah, it's just a foundation that, and we'll just move on.
Yeah.
More difficult part.
Right. Cool. Thanks very much.
Thank you.
Thanks, Rachel. Pretty good.
Thank you.
Thank you.
Thanks, Matt.